Okay, so in today's video we're going to be looking at the initial part of the Moivres Theorem. Okay, so he was a French mathematician, you can Google him, okay, but Moivres Theorem, very powerful theorem when it comes to complex numbers, and you're going to see it's going to come up in more than one or two topics in complex numbers. So we've just seen in the previous video about multiplying complex numbers together when they're in polar form. So if I've got z, which is r cos theta plus I sin theta, well, obviously, if I want to find z squared, okay, that's the same thing multiplied by itself. You'd multiply the two moduli together, so r times r is r squared. And we've seen the rule is you add your angles or your arguments together, so theta plus theta would give you 2 theta, and that's what z squared would look like. Z cubed, well, you would just multiply r cos theta plus I sin theta with r squared cos 2 theta plus I sin 2 theta. R times r squared gives you r cubed, and then theta plus 2 theta will give you 3 thetas. And you can sort of see there's a pattern that emerges, and the main pattern is, in general, if you want to raise any complex number written in polar form to a power, then it's quite easy to do. So what we do is we raise the power of the moduli, okay, and we multiply the argument by the power as well, okay, to get what the new argument would be. Okay, this holds when n is an integer, so positive or negative, but also when n is a fraction as well, okay, which we will see when we look at roots. So, for example, what to do like r to the power a half, that sort of thing, okay, or z to the power a half, I should say. Okay, right, so we're going to have a look at an example just to show you how this works in theory, okay. So it's be done in two parts, so we're going to look at an example. Okay, we're going to let z equal 1 plus I, and we're going to have two parts of this question. We're going to express z in polar form, first of all. That's going to be the first part of the question. So I'll express z in polar form. And part B, we're going to hence show that z to the power 5 plus 4 lots of z equals 0. Okay, so we're going to use that to show that. Now, this question could have just asked us, without part A, show that z to the power 5 plus 4z equals 0, which means I'd have to raise this to the power 5, which would get quite messy. Not the worst, because it's nice numbers 1 plus I, okay, but it would take a bit of time, and then you're going to see it would equal 0, whereas we're going to use polar form just to show you that the Moivres theorem can make the raising it to the power 5 quite a quick process. Okay, so we're going to look at that there. All right. So let's start us off with solution. Okay, so solution. Let's focus on part A. So we want to express z equals 1 plus I in polar form. So we're going to draw out our real and imaginary axis. Okay, now we don't need to consider the negative of this bit because we've just got 1 plus I. So that 1 is the real number, so we go along 1 in the real axis, up a value I, 1i I should say. Let me rub that out. There should be 1i there. So we go up 1 in the imaginary axis, so our complex number is over here. Okay, so we've got z all the way over there. R is the size of it, and theta is the angle that it makes from the real direction. Okay, so that's what we've seen in a previous video, 2 videos ago, and we're going to work out polar form from that. So our size of a triangle is going to be 1 and 1, and therefore we'll work out r using Pythagoras. So you'll actually be able to probably work out that's actually one of your exact value triangles from higher as well. When you've got the sides 1 and 1, that gives you root 2, but to show you that, you get 1 squared plus 1 squared, which becomes the square root of 2. Okay, so the size of r is 2. Okay, the size of z I should say is 2, r is 2. So theta, so remember we're going to work out what theta is, so tan of theta, that equals opposite over adjacent, so opposite is 1 divided by 1, so it's going to be 1 over 1, okay, 1 over 1 is just 1, so theta is the tan inverse of 1 over 1, which you remember from your higher exact value triangles, that gives you the answer 45 degrees, and if you wrote that in radians, pi over 4, just rub that back out again, didn't mean that, pi over 4. Okay, we're okay with that bit so far? Okay, so I'm going to express this in polar form now. So Z is r bracket cos theta plus I sine theta. So r equals cos of theta, which is going to be cos pi over 4 plus I sine pi over 4. Okay, so that's what, oh, sorry, I can put in what r is square root of 2. So that's what r is there, square root of 2, cos pi over 4 plus I sine pi over 4. Okay, so that's part A done. I've expressed it in polar form. We'll now look at trying to prove part B. So part B is going to be hence show that z to the power 5 plus 4 lots of z equals 0. Okay, so z to the power 5, okay, well that's going to be, well, the rule using the Moivres theorem was that it's going to be r to the power 5 cos 5 lots of pi over 4 plus I sine 5 lots of pi over 4 there. Okay, and that's using the Moivres theorem. Okay, so that's using the Moivres theorem. So that's going to be square root of 2 to the power 5 cos, what's going to be 5 pi over 4 plus I sine 5 pi over 4. Okay, so that's what I've got there. I can take this up, the square root of 2, well if I do that to the power 5, you end up with 4 root 2. Okay, and then we've got this here now, cos 5 pi over 4, remember we like theta to be between the range, if we're in radians, between negative pi and pi. Okay, and you can see 5 pi over 4 is out with that region. Okay, we went too far over. So what we're going to have to do is go around the reverse way, which is the negative way. So if I take 2 pi off that to come in the other way, okay, I end up with negative 3 pi over 4. Okay, so that's what I'm going to get there. So that's going to be cos of negative 3 pi over 4 plus I sine negative 3 pi over 4. Okay, so we're okay with that step there, just remembering the range that we need to be in for that there. So we've got z to the power 5 there. Okay, now I want to then put this back into a way that I can prove that z to the power 5 plus 4 lots of z equals 0. Now I know how I can work out 4 lots of z, just times z by 4 for both the real and imaginary parts, I'll get that bit there. But I need to now put this back into real and imaginary parts, but it is already, it's just written in a way that you're not going to remember. This bit relates to the real part. There's no imaginary number attached to this cos 3 negative 3 pi over 4 bit. Sine of negative 3 pi over 4. Okay, well that's attached to the imaginary bit, as you can see. Okay, so that's going to give me my imaginary bit back. But how do you work out without a calculator cos of negative 3 pi over 4 and sine of negative 3 pi over 4? Well, they're both going to be negative, okay, in the region that we're in. Okay, both cos and sine are negative at those bits. Okay, but how we do that is we relate it back to the angle. So if I think about my complex number, okay, and if I want to go negative 3 pi over 4, okay, so that is negative 3 pi over 4 there, which is the same, okay, as negative 135 degrees, okay, which means that this bit in here must be 45 degrees, or in other words, pi over 4. So it's going to be the same value, just the other way about, okay, using your cast diagram information, okay, and we know what cos and sine of pi over 4 are, okay, so cos of pi over 4 from your exact value triangles is 1 over root 2, so is sine of pi over 4 is 1 over root 2 as well. Okay, so we can see that there. which means that when I'm putting this into here, it's going to be the opposite way. So therefore it's going to be 4 root 2. Okay, cos of negative 3 pi over 4. So that's going to be negative 1 over root 2 plus, not plus, I should say negative, sign of negative as well, negative 1 over root 2 I. Okay, and you can check that in a calculator. If you do that in a calculator, you'll get that value as well. Okay. Okay, so if I multiply these together, so I don't need that next step. So if I multiply this out, okay, 4 root 2 times the first bit here is going to give me negative 4. Then the next bit is going to give me negative 4i. Okay, if I multiply that out. We okay with that step there? Yep, okay. So, I have to prove, so that's what z to the power 5 is, so I'm asked to show z to the power 5 plus 4 lots of z. We write that a bit better. Plus 4 lots of z equals 0. Well, I know what z to the power 5 is, that's going to be negative 4 minus 4i. Plus 4 lots of z, z was 1 plus I to start off with. Okay. It's be negative 4 minus 4i plus 4 plus 4i. And you can see everything cancels. And we can show that it does, in fact, equal 0. Okay. And then that's the end of the solution there. Okay, so there's an example of using the Moivres theorem that we can raise something to the power a lot quicker than if we had to multiply out 5 lots of brackets, shall we say, or even use the binomial theorem to do that. Any questions? Okay.